In this video, we're continuing section 6.3 on the unit circle, and we're going to look at some examples involving negative angles, and then later we'll investigate some bounds for sine and cosine. So that'll involve thinking about how big sine can be and how small it can be, and the same thing with cosine. Okay, all right, so let's talk about negative angles. And I want to look at an example. So let's say I have sine of negative 9 pi over 4, and I want to evaluate this. So to do that, I can use my unit circle. So I'm going to draw some axes. And then let's go ahead and draw our circle. Let's go ahead and draw a circle. Okay, so we got our unit circle here. Okay, so up until now, when we've done our unit circle, we've only talked about how we can evaluate positive angles. But here we have a negative angle. So remember that when we have a positive angle, our reference point is at this point, this rightmost point on the unit circle, that's where 0 is. That's where the angle 0 is. And we start measuring positive angles going, this is counterclockwise around the unit circle. If I want to measure negative angles, we have to go clockwise. So negative angles, to measure negative angles, we go clockwise. We go clockwise around the unit circle. Okay, so, and I see that this is something pi over 4, so we're talking about increments of pi over 4. So I know that if I were to go this way, pi over 4, positive pi over 4 is over here. Remember, pi over 4 is the same thing as 45 degrees. 45 degrees. So if I want to go to negative pi over 4, I go 45 degrees, but in the other direction, in the clockwise direction. So negative pi over 4 would be down here. Negative pi over 4. Okay, and I'm going to keep measuring these increments of 45 degrees, or these increments of pi over 4. Okay, so if I go another pi over 4, another 45 degrees, now I'm down here. This is negative 2 pi over 4. So now we've got 90 degrees, or 2 45s. Okay, if I go another pi over 4, another 45, that puts me here, negative 3 pi over 4. If I go another pi over 4 in that direction, that puts me here. This is negative 4 pi over 4. Or I might notice that this simplifies to just negative pi. Okay. Another pi over 4 in that direction puts me here, negative 5 pi over 4. And yet another pi over 4 puts me up here at negative 6 pi over 4. Okay. If I go another pi over 4, well, it puts me at the same spot as positive pi over 4. Okay. So this is where the angle negative, this is where the angle negative 7 pi over 4 would be. So notice that pi over 4 and negative 7 pi over 4, those angles are both at the same spot on the unit circle. Okay. And if I go another pi over 4, we end up back here, and that is negative 8 pi over 4. Negative 8 pi over 4, but that simplifies to just negative 2 pi. Okay, and I think that makes sense because if I go around the unit circle one full time in the counterclockwise direction, that puts me at positive 2 pi. So if I went around in the negative direction, a full circle, it makes sense that would be negative 2 pi. Okay, so to get to negative 9 pi over 4, I got to go one more of these pi over 4s. One more spot in that negative direction. So negative 9 pi over 4 is at the same spot as just negative pi over 4. Okay, so then what I need to know is, at that spot on the unit circle, what are the coordinates? So what are the coordinates of that point on the unit circle? Okay, so for this, either I need to know my unit circle. So if I have it memorized, and we really want to push for that, we want to try to get it memorized eventually. You know, we might remember what these coordinates are. If we didn't quite remember what they are, the key thing that we would need to know is our 45, 45, 90, and 30, 60, 90 stuff. Like I know, for example, that this is a 45 degree angle here. I know, for example, that is a 45 degree angle. And if I just remember my relationships in a 45, 45, 90, I could quickly figure out, well, what is this x coordinate and what is that y coordinate? Okay, so for example, I know the radius of my unit circle is 1, and that's the hypotenuse of this right triangle. So to get the legs then, what I do is I take that hypotenuse and I divide it by, we divide it by square root of 2. So when I divide it by square root of 2, I get 1 divided by square root of 2. So 1 divided by square root of 2, that is this length. Okay, so that is also going to be this vertical length down here. But it's convention that when you use the unit circle to rationalize the denominator, when you work with fractions like this. So if I were to rationalize the denominator, 1 over root 2, let's rationalize the denominator. I will multiply the top and the bottom by root 2 over root 2. Well, that gives me root 2 over 2. Okay, so 1 over root 2 is the same thing as root 2 over 2. Okay, so this is the same thing as root 2 over 2. So this vertical length is the same. It is root, didn't mean to erase that. That vertical length is also root 2 over 2. But because this y-coordinate at this point is negative, I'm going to put a negative sign in front of this y value. Okay, so now I can read off these coordinates. I can read off those coordinates, which are the x-coordinate is root 2 over 2. That's this horizontal length. The y-coordinate is this vertical length, which is negative root 2 over 2. Okay, of course, if I have my unit circle memorized, I could have gotten these coordinates a lot more quickly. Like if I look back up to my unit circle from a couple pages ago, at that spot I'm looking at my angle, well, here are the coordinates. Here are those coordinates, the same values I got. Okay, so I'm just showing you, well, how could we have gotten those coordinates if I didn't have the whole unit circle memorized? As long as I know my 45, 45, 90 and my 30, 60, 90, I can get any coordinate on the unit circle. Okay, all right, so I need to figure out what sine of that angle. Well, remember that sine in the unit circle is the y value. Sine is the y value. And for my coordinate, the y value is negative root 2 over 2. And that's my answer. All right, so let's take a look at another problem. Part B says I got sine, and then I got a little 4 in the exponent, and then I got my angle. So this might look a little weird, but this is how we write exponents on trig functions. What this actually means is we'll do sine of negative 9 pi over 4. Do that first. And then it's convention to write an exponent on a trig function here. What that actually means is do the sine of that angle and then take the 4th power of whatever that is. Okay, so well, we just worked out what sine of negative 9 pi over 4 is, right? We just got that's negative root 2 over 2. And that whole thing we are raising to the 4th power. Okay, so when I raise this whole thing to the 4th power, well, because I'm dividing terms, I get to distribute that 4th power to the numerator and to the denominator. So if I do the 2 to the 4th power on the denominator, that's just 16. That part's not too bad. On the numerator, I will have a root 2 times root 2 times root 2 times root 2, 4 times. Okay, and if I multiply root 2 by itself, well, that's just 2. Same thing here, multiplying these together, that's just 2. So overall, I get 2 times 2, which is 4. My numerator is 4. And then also this 4th power has to apply to that negative. That's technically a negative 1 to the 4th power, which then gives me a positive. That becomes positive. Okay, and then I can simplify this fraction. That is just 1 over 4. All right, and that's my answer. Okay, so that is how an exponent on a trig function where we will see it written. It's written right after the trig portion, before the angle, but what it means is actually this. Evaluate the trig function, and then once you do that, raise the whole thing to the power. Okay, so I want to end this video by talking about some bounds for sine and cosine. So what do I mean by this? What I mean is I would really like to be able to figure out, when I think about sine and no matter what angle I plug in for sine, are there some numbers that sine will always end up being in between? I would love to get something like that. Okay, so I'm going to draw my axes. I am going to draw my axes. And then I'm going to draw my unit circle. Let's draw the unit circle. Okay, not a great picture. Let's draw that one more time. Okay, still not great, but okay, I'm going to go with it. So I got my circle. All right, and if I take a look at my unit circle, I'm going to go ahead and draw some arbitrary point on it. and I'm going to draw a line connecting that point to the origin. So let's label the coordinates x comma y, and I'll call this angle theta. I'll call that angle theta. So I know that sine is my y value on the unit circle. It's this y coordinate. So what I'm going to try to do is I'm going to try to figure out what y is bounded by. Like, can I find two numbers that y is always in between? Okay, so if I take a look at where this point could be on the unit circle, I notice that like this endpoint right here is 1, 0. The endpoint on this side is negative 1, 0. Up top, it is 0, 1. And at the bottom, it is 0, negative 1. Okay. And when I think about my y value, what's the biggest the y value could be at any point on the unit circle? Well, it's up top. Up top, I have the biggest possible y value, and that's 1. So the biggest y could be is 1. What's the smallest y could be? Well, that happens at this bottom point on the unit circle, where y is negative 1. So y is always between negative 1 and positive 1. And we just said that y is the same thing. We just said that y is the same thing as sine theta. Y is the same thing as sine theta. Okay, so I'm going to, essentially, I get to write the negative 1 there and the positive 1 there. Okay, so negative 1 goes here, positive 1 goes there, and I'm going to box that. What this means is when I do sine of any angle, the output is always between negative 1 and positive 1. It can never be bigger than 1, and it can never be smaller than negative 1. Okay, let's see if we can get the same thing for cosine. So cosine, I'd love to figure out when I do cosine of an angle, what is it always in between? What is it always in between? Okay, and I know cosine is my x coordinate. Cosine is my x. So I know cosine is the x value. So I'm really looking for, are there two numbers that I can find that x is always in between on my unit circle? So what's the biggest that x could be? Well, that happens to be at this rightmost endpoint where the x value is 1. So that's the biggest x can be. And the smallest x can be happens at this leftmost endpoint where the x coordinate is negative 1. So that's the smallest x can be. Okay, all right, so that means cosine, because cosine is just x, is in between negative 1 and positive 1. All right, so I'm going to box that as well. Okay, so we have these bounds for both sine as well as cosine. Both of those trig functions, no matter what the angle is, will always be between negative 1 and positive 1 for the output. Okay, so the other trig functions are either unbounded, meaning we can't find numbers like these, that they're always in between, or they don't have bounds that are as simple as these. Okay, so for example, if we look at the trig function tangent of theta, in the unit circle, I know tangent is y over x. Okay, and it turns out tangent is unbounded. There aren't just two numbers that the output will always be between. So one of the ways I can see that is if I let my angle get really close to pi over 2. Remember, pi over 2 is the angle up top, my 90-degree mark. Well, when I do that, tangent of theta becomes close to, it becomes really close to, so I know tangent is y over x. And as my angle gets really, really close to pi over 2, really, really close to this spot right here, really, really close to that spot, the y value gets really close to this y value. Okay, so that y value becomes almost 1. Okay, and as I get really close to this angle, the x coordinate gets really close to 0. So my denominator of tangent is x. Well, that x value is going to be almost 0. Almost 0. So if I have a fraction and the numerator is really close to 1, like imagine like 0.99 or something like that, and my denominator is really small, really close to 0, like 0.000001 or something like that, Well, when I do that, when I divide by something really, 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 really small, it makes the whole fraction really big. It makes the whole fraction really big. Okay, so because of that, we can't really get a number that tangent is always less than. Essentially, as this denominator gets closer and closer to 0, the tangent gets bigger and bigger and bigger. So there is no number that's for sure like an upper bound, something that tangent is always less than. Okay, so similarly with other trig functions, they're either unbounded or their bounds are just not as simple as they are for sine and cosine. So those are the ones that I really want us to know.